Thank you, Pablo. So I start by saying I'm very happy to be here honoring Antonio, and I have a personal story related to that. I mean, I came here in '96. I had spent like 12 years abroad, and I decided to go back to my country, Argentina, and it was a total catastrophe. I got totally broke, and I was almost changing careers. And then I got the invitation to spend a year here from Antonio and the group. And this changes my life. So in a sense, you see here, you have spoken about students that went through the group. Well, there are more established people that also went through the group and for which the group was very important. And I thank you, Antonio, for his creation and all the people around him. Now, when I came in '96 here, I came with a mission. I said, I'm going to teach these poor probabilist guys all the techniques we know from statistical mechanics, which are the real thing, the strong things. And I failed miserably. In fact, it went the other way. They taught me coupling and they made me a probabilist, you know? So after so many years, I decided to give it another try, okay? And introduce one technique that is very useful in statistical mechanics. And I think you should keep in mind if you are dealing with probabilistic problems, stochastic process. So I'm going to illustrate this technique in order to make it more palatable. First with something that has a holy name, so it attracts attention. And then with this is an example of Markov processes. But then I will show you how it can give you some information in a rather easy way on hidden Markov processes, just to illustrate. Okay? So this is work that I did with Evgeny Verbitsky. He works in dynamical systems a la Ruel Bowen. And in fact, it was too much for him. So I wrote it, I did the whole calculations, and then he stopped the publication because he wanted to add more things. So it has been unpublished. So this is the first time I show it to you. So let me start with a general presentation of what the cluster expansion is and what it's good for, mainly on the statistical mechanical front. So in statistical mechanics, we have some object called the partition function, and there are different partition functions depending on the approach that you do to statistical mechanics. And there is something called grand canonical ensemble, that's Boltzmann name, which amounts to a gas of particles that in which you have a variable number of particles. Okay, if you deal with the spin systems, the particles don't change, the spins are frozen there. I mean, they can move, but you have always the same number of spins. When the number of objects can change, you have the grand canonical partition function. I'm going to write the branch. But it depends on some variable which are called fugacities or activities, which in fact they are not really completely physical. They are more auxiliary in the initial formalizations. And in the traditional approach, the interaction between these objects is just hardcore, it's exclusion. There is an exclusion rule that if you violate it, then two particles cannot coexist, cannot be simultaneously there. This can be very general, it can be really, if they are balls, they don't overlap, but there could be colors or other attributes, and you may want some further coordination of attributes, otherwise you forbid them. So it could be very general. Briefly on this history of this thing, at the end of the 19th century, people were not happy with the ideal gas equation of a state, going back to your high school knowledge. So, and especially Kamerlingh-Onnes. So the first correction was done by van der Waals. All these are Dutch people, because Dutch people are extremely involved with fluids, because they are flooded by one of them. So they are very interested in doing a good theory of fluids. So van der Waals corrected and produced a new equation of a state that has his name, but it was which was extremely successful, but it was soon discovered that it was unphysical. There were some problems of stability that the equation could work up to a point and then it ceases to work. But then Kamerlingh-Onnes in Leiden discovered superfluidity. And then he needed a good way to describe fluids, real fluids. So he extended this, he corrected the van der Waals equation into an infinite series of the pressure in terms of the density, which is called the virial expansion. And it was produced as a phenomenological approach. Then people will go and measure in experiments the different virial coefficients, and that describes the fluid. Of course, then people started wondering, can I compute the coefficients starting from first principles, from a microscopic model of interactions? And there is, the coming in honest was in 1910, basically. And then in the 40s, late 30s, Mayer came with an explanation. The explanation was very indirect. He produced first the cluster expansion. The cluster expansion expands the pressure in terms of the activity. Then you take the derivative of that and you get the density in terms of the activity. You invert this last series and you write the activity in terms of the density. You plug it into the cluster expansion, and then finally you get your virial expansion. So it's complicated, and this was the first step in this complicated calculation. But anyway, this first step took a life of its own, because it was discovered that many systems could be written as an expansion of this type. And that's why the technology nowadays, it involves rewriting whatever you want to study in a form like this. And my illustration will be exactly how to do it for this Markov and hidden Markov problems. For instance, this is done for high temperature expansion to describe statistical mechanics at high temperature. It can be done at low temperature by changing variables from spins to contours, Payer's contours. And then again, the Payer's argument ends up with a cluster expansion, but you don't see it. Okay? And there are other perturbative methods and different regions of the phase diagram which require changing variables to other variables, so that you end up with an expression like this. Okay? Okay, so the main issue when you want to apply cluster expansion to a certain system is that one. Determine the convergence radius of your expansion. This in general is a polydisk in the fugacity. The fugacity can change from molecule to molecule, from polymer to polymer, so this is a polydisk. And this is a power series, so once you have a convergence, you get analyticity. So that means many things. One of them, you can differentiate, and then you get all the full control of correlation functions as a series. So you have the dominant terms and the corrections, so it really allows for comparisons. And the linear combinations of the derivatives, you get control of any local observable that you want. But more importantly, you've proved lack of phase transition in the strongest possible sense, which is analyticity, which is stronger than lack of multiple Gibbs states. It's more stronger than uniqueness, because there are other more subtle phase transitions in which the pressure or the free energy is smooth, in fact could even have infinite, all the derivatives, but they grow too fast to be analytic. These transitions occur, and this shows that really analyticity is the strongest way of phase transition. And furthermore, through the series that you obtain, is completely explicit. You have an expression there. You get everything you want, basically, including boundary finite volume corrections. Okay. Now, how do you use, what is the type of the approach? There are two steps in the approach, in the use of this technology. The first one is the tough one nowadays. The first one is where you have to use creativity. Is you have your problem and you have to somehow handle it so you can write it as a partition, as a grand canonical partition function in terms of some fugacity of some type of molecules, or called polymers, if you're lucky with only hardcore interaction. This is the standard case, which is the only one I'm going to consider today. But once you do that, then the rest is automatic, because you're going to take the log. Okay, that's what you do. You take the log. Why you take the log? because the log has nice property. When you take the derivative of the log, you get expectations. So you get everything you want. And also, when you take ratios of partition functions, which is what usually happens, if you can develop the log, you get the ratio as the exponential of one log over the exponential of the other, and the exponential can be subtracted. And then you have a lot, you can show a lot of cancellations that way. So it's extremely flexible to go to the log. Now, you can imagine this is an expansion, and then you take the log of an expansion it's a multivariable expansion, infinitely many variables. So this could be a tough part, but this part now is well known. We know how to go from here to here, completely explicit. Okay, so we know the combinatorial expressions, and there are many approaches, and I'm fan of one of them that I developed with Aldo Procacci, which that determine the region of convergence. Okay, so this is the main advantage of the use of the cluster expansion. Okay, you have to use creativity here, but once you have it, the hard part is automatic. You take it from the shelf and you apply it. Okay, so let me do the general setup. So the general setup, I have a countable family, infinity, but countable, of some objects that let's call polymers. Dobrushin wanted to call them animals, other people call them molecules. Basically, these are objects that are not very simple. They are formed by combinations of other more elementary objects. You will see in the examples that I present here. I'm going to use the letter gamma for each of these objects, and then you have an incompatibility constraint. So there is some relation that prevents two things to be together. So this is being compatible and this is being incompatible. And I warn you that people in graph theory, because this will be once you have an incompatibility relation, you have a graph associated to that. You give me several objects and I draw a graph with these objects as vertex and links every time they are incompatible. And this, people in graph theory use it, but then they use the opposite sign. If they are connected by the graph, they use this one. I use the statistical mechanical one. Okay, and I'm going to use that each polymer is incompatible with itself, just for simplicity. Otherwise, you have to sum all the different copies, and it's a renormalization of the fugacity, so it's not really, you don't gain anything. Okay, so here fugacity, activities. And then you have a family of activities that I'm denoted here rho, and maybe I will denote with other letters later because I took some transparencies from other talks, so there will be a lot of symbols meaning the same, a way to keep you awake. Okay, so these are the families of activities are given. This is part of the model. So you have the definition of polymer, the definition of compatibility, and then the activity, which are the weights. And with that, this is the grand canonical partition function. So you sum over all families of polymers, any number. So I write 1 over n factorial because this is an ordered thing, and these are all different because I consider they have to be compatible between themselves. And I consider you cannot have two copies of the same because each one is incompatible with itself. So this is the same as taking out the factorial and putting here curly brackets, set of n polymers. Now this is better, I use this because, except in one case, because when you go to the log, I keep this way of summing, and at that time I cannot do this change into curly brackets, okay? See, this is any pair of I'm summing over n of them. This is j less than k, both from 1 to n. I didn't write that. Okay, so this is a very simple interaction. You have a fugacity which tells you how favorable it is to have this polymer there or not. And then the compatibility, the interaction between them is you are authorized or you are not, each pair. That's it. It's simple. I think this is an ideal gas with exclusion. That would be what Van der Waals tried to describe. And I think this could be kind of a Poisson process if you write it in the right way. The most elementary thing you can have. And the idea is, whenever you want to apply, write it that way, with some gamma, some compatibility, some definition of gamma, and some definition of Z.
It is a Poisson process conditional
to
compatibility.
Okay. Very good. Yeah, if I didn't have that, it would be Poisson. But the condition to compatibility. Very good. Yeah, maybe that's what I should write. Eh?
It's a Poisson process conditioned to compatibility. So that if you have points that cannot be at distance less than 1, you condition that the points are farther than 1 each pair. But here is more complicated space, but you have a notion of compatibility.
Okay, we discuss it later, but this is interesting. I mean, maybe this is another way to sell it. You know?
Because of the support condition, the union of the supports of the gamma I must be lambda.
Yeah, so here there is a lambda. Lambda means, and there is lambda here. So I mean, I take a finite family P lambda that in many cases is related by the object has to be inside a volume, a region.
Expansion is finite.
This expansion is finite. This expansion is finite. But when I take the log, it's no longer finite. Okay? So this is okay, this is finite, this is analytic, no problem. Because P lambda is finite. Of course, my interest is to go to lambda equal to infinity, which like that, it blows up. But if I take the log, then it blows as the volume, and then I can divide by the log, and there is a density. What?
And allow repetitions.
Yeah, but let me go to the log. Just don't spoil the film, you know. So this is what I need to do. That's where all the artillery when using this expansion is to write whatever you want to estimate in this way for an appropriate set, an appropriate compatibility condition, okay, and an appropriate notion of polymer. And this we'll see in the examples how you do it in this case. And then you take the log, and that's your goal, to control the log. Now, when you take the log, even as a formal power series, you go into an infinite series, even if this is finite. Take the log. I mean, you take 1 plus epsilon, 1 plus z, which is this, when you have only one polymer present, you take the log, you get an infinite series. Okay, with that, you get an infinite. And that's what you want to control, to show that this converges as a power series in this multivariable z. Another thing that you do the weights. Here, it depends on how you interpret it. So if you want the probability of having exactly gamma 1, gamma 2, gamma n, this is the probability of having them divided by the partition function. You could ask by the probability of having them present, so there could be other ones. Then you need another partition function here of all the other possible polymers that are compatible with this n. And this gives you the idea that the ratio of partition function plays an important role at the level of these probability weights. And you are interested in the lambda going to infinite limit of these probability weights in some physical applications, but not always. Okay, so that's the heart of the matter. Write it that way. You are interested in the thermodynamic limit, and in particular, if you control well the cluster expansion, which is the expansion of the log, then the log divided by lambda will converge. These weights will converge and define a measure in infinite volume. And then you can even have the asymptotic behavior of the partition or its log when lambda is very large but not infinite. All this you get it through the expansion. And here is the thing that is automatic. So it may look a little bit impressive, but this is well known. You don't need to even to know it. If you take the log of that expression I wrote before, it takes this form. This is an identity. So it's the same as before. It's a sum over 1 over n factorial families of n things with the fugacities. But the weights is not the product of the indicator functions. It's much more complicated. And this is the way, this is the hard line. So the idea is the following. You have to consider the gamma 1, gamma n, and consider the graph formed by incompatibility. So now it's the opposite. What you want here, these have to be incompatible. Otherwise, the log, they don't contribute. So you consider the graph defined by incompatibility. This is the big G here. It has to be connected, otherwise the contribution is 0. And then you take all possible subgraphs of that, which visit all the vertices and are connected. And for each of these graphs, you sum -1 to the number of links of the graph. So for n large, you have a huge sum of terms of alternating signs, ones and -1s, which is the tough thing to handle, because if you put absolute value inside, this blows up. So you have to take care of these cancellations in an efficient way. And that's what made the proof of convergence something delicate. In fact, Mayer didn't care, physicists didn't care, and then there were people that started worrying about that, and they had a very bad way to prove it. Then there was Camarota that said the good way, Bridges got it a little better, and then from there, Kotesky Price, Dobrushin, and then finally we understood how better you can get. So, but this is known. So you don't even have to know it. I mean, you know, if you take the log, there's going to be this behind, but you don't need to know. But you want to know the convergence of the log. And this is the criterion. So I'm going to tell the criterion I developed with Aldo, which explains all the other criteria. And the idea is very simple. Penrose, before that, Camarota, they proved that these sums of terms can be bounded in terms of sums of trees, where the diagrams are trees. Okay, this is I'm skipping that part. The proof is not complicated at all. So basically, what you have a situation like this. And you want to put, so I'm going to take absolute values. So I'm going to put absolute value of the fugacity. So I'm going to call lambda the absolute value, which this is lambda is a positive value. The fugacity can be even complex here. Lambda is a positive value. So you want to put lambdas here. And the argument is the following. Consider a single, and you can see that the condition is that in each vertex, the different polymers that you put in the vertex, forming the graph, have to be compatible with themselves, between themselves, but incompatible with the root. So you take only one per generation, okay? Here you have lambda, and here you have mu. You put a mu, okay? And what is the idea? If you take a first generation, so these are polymers that are incompatible with the root, but compatible among themselves. And you replace mu. In the beginning, you have the lambda, which is here, which is multiplying the phi. So you have lambda times phi. So the idea is, suppose that you do here, and you find that when you sum over all the possible assignments of polymers, this is less than mu. This is gamma mu gamma. If you get this, then what you have? In this thing, when you put mu's there, this sum is bringing the mu down there. And you can continue by induction, and you end up that the whole thing is less or equal than mu, whatever the number of generations. And this is a sum of positive terms. This is sum over trees. So you are proving convergence. That's it. You see, it took a long time for us to understand that. And it's if and only if summation, because for the only if, you take as mu the sum over all the trees that follow. So this is the way to prove convergence of positive terms on trees. Okay. Now, historically, people ignore the fact that these things have to be compatible, so they got the most elementary thing, you got an exponential there. That was Kotesky Price. Dobrushin said they have to be different. Dobrushin produced a 5-line proof of the convergence that is better than Kotesky Price, but doesn't use the expression. And this was the thing that tortured us with Aldo. Cannot be, you know the expressions of the expansion, and even knowing it, Dobrushin, with one inductive argument, gets better than you. What's the problem? So Dobrushin was getting better because he realized it, without really realizing, because he did it inductively, that you have to propose that the things you put here have to be different. With Aldo, we realized that the real thing, they have to be compatible. When you put compatibility there, here, instead of just being different, this is your convergence criteria. Find the mu such that this ratio is positive, as big as possible. Maximize of a mu, and then we improve Dobrushin by a lot in some cases. So you see, that's the point. Once you have your gammas and your compatibility, you produce this sum, which is just a one generation tree, okay? And find the mu for which mu over phi of mu is maximum. So that's the other part where you have to do some dance, which is some algebraic, in general, elementary considerations. I'm going to show an example how you do it. Okay? And then that's it. That's the point. So once you, I think I write it here. No, I'm sorry, I'm going back. What am I doing? Here. So once you have this convergence, then you can write, for instance, the log of the ratio when you have one polymer less, which is what happens when you condition, for instance, in Markov, the transition probability. Then you see, you have the log of sigma minus the log of sigma minus un contour. Here, you have all the clusters in lambda. Here, all the clusters in lambda that don't contain gamma. When you do the difference, you get all the clusters that contain gamma, which is a mass reduced sum, and you have a full control of that. And you can even, with some operations that I'm not going to describe, you find errors. See, this is a bound that is independent of lambda, which is more or less an uniform finite volume correction, okay, or for the log. So these are the rules of the game. First step, write a partition function as a gas, as a Poisson conditioned, a conditioned Poisson. And then go and try to maximize this ratio. End of it. Okay, so in a sense, many people hate the cluster expansion, but when they do, they develop their own expansions that they understand better and they claim that's better. But then, say you have a proliferation of expansions adapted to different problems, each one with its own rules, and only work for that problem and not work for the other. So why not give it a try to a universal thing, well tested, from which the harder part is already there, is safe. You're not going to do a mistake. You're not going to have to retract your paper. It takes the effort of writing things in the gas form and then checking the convergence condition. That's all. Okay. Now, a particular case is when the polymers are subsets of a lattice. For instance, in a lattice gas, and as we'll see also in the Markov and hidden Markov applications. Okay? In that case, being compatible means not intersecting. So this first, this phi, becomes the sum over all the gammas that are not intersecting among themselves, but they all intersect the root. Okay? And the convergence condition becomes this. Okay? And then we do a simplification that leads to, in fact, to another part of the story. I'm gonna forget some of these conditions to replace this sum by something bigger, in which the only thing that I say is they have to intersect the root, and they have to be compatible among themselves. From this, the only thing I'm going to retain is that they have to intersect the root at different points. Otherwise, they would be incompatible right there. I keep only that. I don't see what happens later, which they also should be disjoint. I don't consider that. Therefore, the number of polymers you can put here cannot be bigger than the size of the root, because you need 1 point of the root per each polymer that you add. And then, how do you choose these points? Well, you have a combinatorial factor. You sum over all choices, and you get this condition, which is simpler. Okay? And the idea is to find a mu for which this is satisfied. And then there is a traditional change of variable that comes historical. For us, it's better that way, but historically it was not that. in which you redefine mu as lambda times mu to the gamma. This is a single parameter, which in fact positive parameter, and this is the size of the contour. So if I replace this here, I end up with this expression. And this expression has the advantage that the only thing I have to optimize is this parameter mu. You take derivative equal to 0 and find it. It's much more workable. Now, this expression has been obtained before by Gruber and Kunz, not using the cluster expansion, but using another technique called Kirchhoff-Salzburg equation in a paper that nobody read. So they were desperate. I was in Lausanne when they were there, because all the people were celebrating Dobrushin, or before that Kotevsky Prize, and they said, but we can do it better, because this is better than the other two. This is not better than ours because we are forgetting some. Okay, the only difference is that what they did, they had to introduce an artificial, and that's a deviation of the people that worked in that. They knew too much mathematics, so they wanted to use fixed point theorem, so they introduced an artificial Banach structure with some norm that they invented, and then you have to prove a contraction there in the transformation with a contraction, so they obtained it with a strict inequality. We said, but we only need to be bounded because it's a positive series. We didn't know that much mathematics, so we could incorporate the equality. So that's why it's GK plus. Okay, Gruber Kunz with a little bit of us. But in fact, they knew it. They knew it. But now we can explain it, what they were doing at this level. And I'm going to use this one for our application because it's easier to work. Okay, so I'm not trying to optimize. I'm just trying to show that it could be useful. Okay, so the first application, this is due to Dobrushin. Dobrushin wrote a posthumous review on cluster expansions, in fact, which he has another name, animal expansion, something like that. These are notes of Lesouche, I think. But he died before writing it, so his wife completed it, and it's one of the most perfect examples of broken English. I mean, this is impossible to understand. The English is a catastrophe. But there were plenty of ideas, and one of them is this one. Nobody read that. So you take a Markov chain, and the point is it's useful for inhomogeneous Markov chain, so that you don't need two copies of the same. Okay, so I use this notation for a sequence of symbols or for intervals like that. And then what he said, you see, I had another point. I kind of defended the ignorance of the probabilist in not using the cluster expansion because I said probabilist people don't care for analyticity because everything is positive. Until I realized that it was false, because probabilist people prove the central limit theorem, and there they use the characteristic function, and then they have to go into complex numbers. So, and that's what Dobrushin is doing. Let's take a bunch of functions of the sides of the different points, and let's construct this, where this side could be complex. And that's what you want to show, that this is analytic inside. Okay, that's the goal. So he uses a trick that is the one that invented Myers in the 40s, which you write a sum as the product of the terms, and then you add and subtract 1, as it is often done in mathematics. So you are adding 0, and then you expand, and you label the terms of the expansion by those that for which you choose this part. Sn, you get at some weight alpha of each side, xi. Okay, at each you introduce a term e to the alpha xi for each xi in your progression. You choose any alpha of xi, depending on what you want to do. No, you put it on top. Suppose that you want to prove kind of a central limit theorem. You have to do e to the I sum of random variables. For instance, it depends on what the x are. Well, if this is real, it will be, but in principle, you want it to be complex even. For the same price, it can be complex. So it can be the Fourier transform.
Okay. Just wrote it down.
Yeah. Yes, that's basically the idea. I mean, yes. No, for this is only one. If you two functions, you would incorporate it into those, and then you're gonna do analyticity with respect to p's. But for this application, I just want to show, and I'm gonna go very far. I'm not gonna go very far because the conclusion, the evolution gets very messy because he used his criterion instead of our criterion. But in order to use our criterion, I will need a graduate student that does the hard work. But so I am not going to complete that. But I'm going to show you another one in which I did the whole thing. So then you end up with a sum over families from these endpoints. Some of them are the families in which you choose the alpha xi. Okay. And then the sum that you end up with something like this, where this high is, no, let me go to the next one. What am I doing? There. This is high, okay? But then you need this thing on full intervals to decompose into little pieces. So what he does is write this as the difference plus p. And use the PA as part of the next one. So if you do that, and let me go a little faster here, but just to prove a point. He writes the thing as the sum in which you have these differences, this term minus the previous one, and this becomes a gas expansion in which the fugacities are this form. So you see it's a long sum, and what enters is the mixing properties of the chain. So in order for fugacity to be small enough, you need sufficiently mixing properties, and then he ties up the analyticity of this expression that you want to the mixing properties of the chain. And I'm going to stop here because I prefer to say the thing which I did the calculations in detail. But just to show you that cluster expansion has been applied by Dobrushin to inhomogeneous, to the central limit theorem of inhomogeneous Markov chains. Yeah, I'm not expecting you to fool. The conclusion is to do the calculation, which is the condition under which you have it. And that's a mess, and I don't want to do it. I just want to show that you can write even a problem Markov things as a grand partition function of some partition, which is some fugacities, which are this, and the constraints are the intervals cannot, you are taking intervals that are disjoint. Let me go to the next example. This is to mention Dobrushin. That's why I include. This is not a given state. This is a sum. Yeah, but okay, so let me go to the next one. This is not so well known that a hidden Markov is a given state, depending on what is the hidden Markov. Okay? So let me go to that. I have 20 minutes, so let me do this in detail. I think that hope these two. So the thing is the following. I take a Markov process. That's the one that is going to be hidden. I'm going to consider shift invariant, ergodic, and not null in this strong sense. All the transition probabilities are larger than a little p. Okay? And very often I'm going to use, because this Evgeny comes from dynamical systems, so I like to condition with respect to the future. It's the same to do with respect to the past. It has to be. No. Larger or equal. Larger or equal, sorry. Infimum or mean. I'm missing the mean. Sorry. P is the minimum of all of them. It has to be strongly non-null. Otherwise, the thing doesn't work. And then on top of that, I put what is called single channel emission matrix. Okay, which each x that is produced by this Markov process transforms into a y at each side. The conditions on Rxy has to be positive, the sum has to be 1, and in general, this is the hidden Markov process. I'm using the letter y, so the probability of the hidden, the y, is obtained by taking all the x's generated by the hidden one, and each of them asks what is the probability that each of them is flipped to the y you want. Okay, so this is the standard definition of a hidden Markov chain. Now I'm going to use the low noise hidden Markov process, and I'm aware that I cannot use this acronym in Argentina. Okay, which is the R is the form do nothing plus an epsilon do something. And this do something is negative. And what you need for this whole thing to be positive or non-negative and some 1. So this is the matrix. The most popular example is this binary Markov chain with binary corruption. Okay, so the Markov chain -1, 1, and it has this matrix transition. So with probability 1 minus p, you stay. Probability p, you change symbol. And then on top of that, you put an R that with probability 1 minus epsilon keep the symbol that the chain had. Probability epsilon flips it. Okay, this defines a hidden Markov process that is well known and well studied. Okay, so it's the same as saying that the hidden is x times a z, where you have epsilon and 1 minus epsilon. Yeah, so, but this is a particular case. The treatment can be much more general. But this has been studied. Now, what are the questions that I'm going to answer with the cluster expansions? So you want the G function, which is conditioned on the past, the possibility of having for the y, y0 now, and what happens when the past goes to infinity. Okay? To know that there is a limit which will be define the G function. The same for the future. And then for two sides, which that would prove Gibsianness, conditions to both sides. And there is another thing that is very interesting to people in dynamical systems, which is the entropy. The entropy is defined as an entropy density, Q log Q. By telescoping this and using the 1 over n, you end up that this is the same, the sign, forget it, doesn't matter, of Q log of the condition transition with respect to the future. That's why they are interested with respect to the future. So basically, and this is the object that they want, so this thing becomes important because this is the thing that is behind all these questions. Okay, this is an overall average. So these are things that have been observed numerically and also by ad hoc studies for different hidden Markov processes. This object exists and an analytic for epsilon small. Okay. Moreover, this form a set of coefficients. So in general, when you stop in n, you have a form like this. It's an infinite series anyway, because I'm taking the log, that converges to an expression which has some stabilization properties. So for each n, there is an n of k such that if you are looking for the kth coefficient, after you exceed n of k, you got already the final coefficient. So the coefficients freeze into the final value after a while, which changes from order to order. This has been observed and proved by ad hoc methods with different stabilization properties for different type of hidden Markov process. Now the problem of the existing proofs that they are ad hoc, different Markov process, different argument. The coefficients require stabilizations in order to find the expression. So they have to prove stabilization first and then find the coefficients. And they don't care for radius conversions. There exists an epsilon and stop there. Now with the cluster expansion, what I promise to do, well, first of all, not ad hoc at all. I'm using this universal approach. Second, I can give you the coefficients right away and prove stabilization by looking at the coefficients. So you have a geometric, in fact, it's a geometric stabilization, explanation of stabilization. And then I give you explicit estimation of the radius of convergence. And therefore, through the finite range corrections, I can give you an explicit estimation of how far off you are of the limit if you stop at some point. Okay? So this is the promise. So now let's see how you do it. So I have to take this object. I'm going to take this object and I'm going to write it as a gas of polymers. That's the main thing to do. In fact, not exactly this object, but almost. So okay, I start. So this is P multiplied by the T, the 1 plus epsilon T. And then you see I distribute. So I call B the points, the i's for which I select this factor. For all the others, I have the delta. So then what you have is in this series, in this probability, all the things that I have the delta I fix it in Y. Only the x's in B remain summable. But then I have these projections. Okay? So what I do now is I multiply and divide by P of Ym, P, top and bottom. And then what I get is I get a sum, epsilon is here, epsilon to the size of B. And that's the coefficient that I get. Okay, so for each point in B, you have the epsilon, the T, sorry, I should remove the epsilon there. And then you have this ratio. Okay. But then you notice that, so you have your set B is formed by disjoint pieces. Okay, and in the middle, you are fixing Y. So the only thing that I care is when I do these probabilities, is for each piece up to where it arrives, and then I use the Y immediately outside. In the middle, the Y is fixed. So then I can factor this term as a factor of the piece in each of these little intervals in which you don't have Y, you have you are summing X. And this is going to be your polymers. That's why I write them. These factors, and then you get that. If I divide by this P, I get a sum. There is a compatibility relation, which is just non-intersection. The polymers are segments, and the weight of the segments are here. Okay. Once I have it there, I know what the log is, and I know the condition for convergence. So this set, I'm going to transform it into a lambda, put absolute value here. The epsilon is, okay. And so the log takes this form. Now I have the expressions of the powers of epsilon, which is summing all the clusters whose total support is of order k, is exactly k. So all the segments whose sum is k. So that's the expression of the generic term of this quantity. But then you have the following. In the clusters, things have to be incompatible. So if I take a bunch of things, a bunch of polymers, which are incompatible and whose total length has to be k, then these polymers, if the total length has to be k, that means that the total length of the polymer is less or equal than k, because they are overlapping. So when I write the sum over polymers, what happens beyond k, I don't care. So if you go to n that is larger than k plus 1, because I need the next one, the expression for the coefficients is the same. Because I'm summing only over polymers whose total area is k. So I prove stabilization in one go by looking to the expansion. And now what about the convergence? I don't have a 1 hour. Huh? 15 minutes, okay. So I have to do a bound of this, first of the fugacity, and then I do it while the epsilon is there. And what I do is this is larger or equal than the little p to a power. This less or equal than 1. And if I sum this, I get 1. So I end up with this bound. And then I have to do this thing. So I replace here that. I get a geometric series, and I'm going to be quick because I have 2 minutes. And I use the formula for nxn, which is an exercise to terrorize calculus students. Okay, you have to take the derivative of the sum of xn. And then you end up that your condition is this, and this you get the k, which is the value for epsilon, less or equal than this expression. So now you see what you have to do. You have to find an x that maximizes this expression, and this determines the radius of convergence of your series. Okay, so this is, I call it x hat, and that's the k. And then you do some numerics, and depending on what p is, I got some numbers. So you really get numbers on k, on the epsilon for which you have your convergence. So numerically it's meaningful. It's beyond proving just existence. Okay, and then you can do for logs, you have to add the x, that's why I included. You have the corrections, you get the full expression. Okay? So just to finish, this is the advantage that we get. We get a universal treatment, a thing with which we feel comfortable, we know how it goes, we have complete control of a series, full level of detail, there is a rich theory of convergence and of transformations, and it gives numerical estimation. Now, of course, you cannot do better than ad hoc methods, and you have to work. You have to be able to represent as a gas of polymers, and you have to be able to deal with this convergence condition. That's the easy part. The hard part is this representation. And I stop there. I finished my pitch.
Thank you very much, Roberto. Is there any question or comment?
Yes. Yeah, that's part of the proof. That is an infinite order, because you prove that there is conversion. Yeah, yeah.
Want to do, for instance, statistics on it, but since life is finite, you can only observe a finite sample. And then you want to have a finite model which approximates. So you have it.
This is finite. I stop in M, stop in N, I have some bounds.
So if you compare with our result,
I don't know, I didn't compare it.
we did it.
My point, no, but my point in this talk was not to show that you get better than what people do when they do ad hoc study. It's that you can also study this way. Yeah.
We wrote a paper, 2 papers on this kind of question. So I'm interested that if this way, which is more complicated than ours, give a better result. Otherwise, I would say, well, thank you very much, but I'm not interested.
Well, no.
Is it better or not?
You know, the point is the following. It never can get better than techniques designed for particular models. Can never get better. But the point of this is that you can get,
Not particular models,
well, particular families of models.
with
Yeah, okay, this works in probably more generally than vast decrease of memory, because I don't know how much I use it, I don't know. But the point is that it's a technique that always works. You take a new model, if you manage to do this, it will work. If you take a new model that is not part of your treatment, then you have to see how to adapt your treatment, if at all possible. That's the only point. That's the meaning of universality. That's all.
using Kalikov expansion. Can you compare it?
Kalikov is more delicate. I need finite range to do what I used there. If when you use Kalikov, you have to separate between the dominant part and the residual part, and then you have the dominant part is like the exclusion one, but the residual one creates a two-body interaction between polymers. Then you have to do an improvement of that, and there are expressions for that. But then I didn't go to that point. I just want, my point here is very humble. Tell you, this works. If everything else fails, think in that. Let me give it that way, say it that way. You see, and I think it doesn't pay to ignore it. It's there, it's working. Has been tested in other situations. It gives you some information that maybe you cannot get immediately with your method. But I didn't sit down to compare, because that was not the point. I don't want to say that this is better. I want to say that this works. That's all, that's all. So you should look to some techniques that people in statistical mechanics have developed.
Using Kalikov or canonical macro.
Yeah, it's a fair question. It's a fair question. But then again, it's not for improvement. It's just for the fact that it's universal. I can probably, the same proof works for our Kalikov and for other things that are more general than that, because you get the same polymer expansion. So you gain in that way. Renato. Oh.
Try to apply it or can it be applied to Markov processes with random environments?
No, I have not tried, and this would be a nice try. But probably you cannot escape at least one renormalization, but don't at the level of the series. Probably, but I didn't try. And then again, I mean, these are things that I did long ago, and if they were blocked, stopped, and then I was working with people in probability that didn't want to hear that. So I mean, thank me for coming back to that and being able to tell you that maybe you should look at this. But this is a good point. What do you do if you have, on top of this, if you have disorder? Okay, and it should help, because it's easier to do the renormalization at the level of this series, in my point of view, than on the original thing with contours and things like that. I don't know, this is my point of view.
What about the application of technique to more general Markov process, say on a tree?
Well, on a tree it shouldn't be very difficult because you have a tree anyway underlying the whole thing. Okay, so I don't know. I was never particularly interested in processes in trees because they are very pathological from my point of view, because they are not amenable graphs. But it should be applicable, should be. But see, we didn't try every possible thing. Our point was not to see how many applications of cluster expansion, just to some benchmark cases that you were interested to show that you can use it. And then we leave it to the general public, especially the students, you know?
Any other question? I have a question.
Can you go two slides back on you got the estimates on the...
This one?
Yeah, to see you just flip it through this.
Yeah, because I have only 2 minutes. I mean, this is the value of epsilon up to which, the epsilon of the flipping thing, up to which you have guaranteed analyticity. It's a number. This is better than saying there exists an epsilon for which. Okay, now, the lower bound, the positivity lower bound, that all transitions of x have to be larger or equal than little p. Yeah. P is equal to 1, no, p equal to 1, that means that you are constantly, you don't flip. The x, the initial, so p is the initial. So that means that it's constant, you start and you continue. That's an extreme case. And this I did some sample calculations. I mean, of course, as you see that the tendency, when you smaller the p, the worse the k, because this bond on the p on the denominator. No? That's the point. With long range, you have to do polymers that, besides the hard core between the dominant part, have a two-body interaction. The theory exists. You have to be careful how you deal with those and how you balance the contribution of both, how you divide what is the dominant and what is the residual one. And there are specialists here that have worked on that for one-dimensional systems. And it's complicated, but in principle it's doable. And in fact, all the work in long range is some type of cluster expansion disguised. Pablo.
So, no, my question is a bit naive. Can you give some interpretation of these polymers? Because it's a black box, as you say, dwarfs use it, but you don't understand what you're doing. It's like algebra.
I would say that you interpret the polymers as the part of your interaction, let's use it that way, that glues somehow the different ingredients in your model. But you have an expansion of that. So it's like you are expanding on on clusters of things that are glued and then are separated from, and then you move on. So the answer is no in general, but you can get it for each particular application once you write it. For instance,
For instance, for the polymers in the one-dimensional case, epsilon, p, etc.
yeah, which are segments.
How do we interpret them?
I don't have any other interpretation in this case. I mean, it's not.
The calico, the composition, you have a very clear interpretation of what is going on.
Because you think in conditioning further and further.
You have a realization of the process in terms of uniform.
So, I mean,
and here, something similar should happen.
you do this. That's the more than I can tell you. Okay, so you end up with y on a non-connected interval. So there are pieces.
I think it's where you fail to make the noise that you divide. It's like at the end should be a calico of the composition that
In the spaces of maybe, but I'm not using. Yeah, okay.
No, you are not using it, but you could.
Maybe. I cannot tell.
Okay. Any other question? Okay. Okay, next speaker is Ricardo Freiman. We'll talk about quantitative Epps theorem and multivariate Bernoulli distribution.
Okay. Okay, thank you very much for the invitation. And at the end, I have some real data applications, so if necessary, we cut it. Okay. ¿Está puesto? It's okay? You hear me? Yeah. Okay, this is an honor to be on this great workshop for Antonio. I choose some pictures that I stole from the network. Yeah.
Steve Jobs.
Okay. Okay, this is joint work with Leonardo Moreno, who was a former student, and with Thomas Ramford from the university. He's in Canada. We had worked before with Thomas several years ago. Antonio has used some of our results, but we never met. And well, what I will talk today is has been published 1 month ago on GRR, on the Royal Society. So the summary is, I wrote a lot because of my English, so you can be sure that you can understand. So the summary is, we use some extensions of Hepes theorem. I will later on put what is Hepes theorem, because it's a nice result, but it has only 50 sites, although it's a very interesting result. That he used on finally supported discrete probabilities. And then we will use for some statistical applications like classification and testing based on projections. In particular, we have some surprising, some way results that in the case of where the support of the distribution is known, for instance, a well-studied example is multivariate binomial distributions where marginal are binomial, but you have correlations. And with only one single projection, then you can determine the distribution. Well, why we are interested in this, in using projections, in particular to one-dimensional directions? Because on high-dimensional problems, statistical high-dimensional problems, if the dimension is high, then you need a huge size of sample size. Particular, most of the non-parametric methods do not work because neighborhoods are mainly empty. On the other hand, if you project them, you are in dimension 1. So at each projection, if you have 100, 200 data, it's okay. Okay. Well, in particular for learning, most of the k-nearest neighbor or kernels method doesn't work in high dimensions. That's because you are looking at small balls in a high dimensional space. And that's where people use random forests or support vector machines to try to deal in this. In particular, there are just a few procedures that are well designed for discrete data. In particular, there is some result of Nedel et al. In 2018 that they consider a classification where the rule is updated, but on hyperplanes but are determined by the original x's. So they use the original coordinates. So we propose a competitive procedure, and we will apply it to testing and learning. And it also provides a general dimension reduction technique based on the bound on the total variation distance between probabilities in terms of the distance in lower dimensions. So you can use it also for clustering or defining depth functions in high dimensional data. Okay, so the idea is to do extensions of Cramer-Wald theorem, who everything knows. See? And there are several extensions, depending on what you assume about the measures P and Q, and less about the set of lines where they coincide. Okay. For instance, we have worked in our previous work, we show that it's enough with looking at a set of directions that have probability 1. For instance, if you choose them on the uniform sphere. And also Rengi in 52, Gilbert, Belize et al., and ourselves have worked on this problem. But this was not for discrete variables, that for general probability measures. Okay, here is a Hepes theorem. So he considered P and Q two probability distribution supported on finite sets. And he showed that is what I call here theorem 1, that is say you have a discrete distribution with support of size k. And if you consider k plus n subspace of dimension m1, mk plus 1, such that no two of these subspaces are contained in a single hyperplane, that is, there is no arbitrary straight line that can be perpendicular to more than one of the HE, then P is equal to Q if these projections coincide. And there are a finite number of projections. Okay? And this was in 1956.
But as many projections as points.
Yeah? I'm sorry?
You have as many projections as points in the space.
Yes.
Mm.
Yes.
One more.
Yeah. Well, we can refine this. That's the point. Okay. Well, there is an example by Rengi that the minimum k plus n is sharp. on his theorem. But an important point is that the dimension of the ambient space plays no rule. It only depends on the size of the support. So we can be in very high dimensional space. If the support is not very large, then it works well. And also, you need only to make a...
Then you cannot find your subspaces, right?
No.
Okay.
No.
No, but
No.
then there's
Yes, yes, you need the...
D to be big enough to,
No, bigger than 1.
but even in dimension 2, you can find, I don't know, 10 subspaces.
I'm sorry?
Even
Yes,
in
there are...
dimension
You have infinite solutions to this problem. Yes? And interesting is that you make assumption on P, on Q, and not on P. So if you are testing Q should be the null hypothesis and P the unknown distribution, there's no assumption about P. Well, and then what we do is we first establish a quantitative version of this Hepes theorem where we bound the total variation between P and Q by the total variation of the distance in the projections. And if you know in advance the support of the distribution, like in the multivariate binomial distribution, the support is known, then we show that it will be enough with only one projection, one-dimensional, only one. Okay. And this projection needs to be chosen to avoid a finite or countable numbers of bad directions, but almost all will work. And well, I will provide then an example, dimension 2, where only 4 directions are the bad ones. Okay. Then we apply to some statistical problems, and we propose a new method for learning from projections and adapt it what is for learning problems for what is called discrete tomography. Have you heard about discrete tomography? Well, I will explain it. And next we consider testing and do some simulations. I don't know if I will talk a little bit of this. That is the problem when I have a multivariate Bernoulli distribution, but I have a sample of size 1. And then the problem is, can I say something about this with only this information? Well, and then we illustrate with simulations and 3 real data examples. Okay. So this is notation. We consider the total variation distance between 2 probability distributions, and we consider the induced probability of the projections over H. And it is clear that we have this large inequality, and we want to have some reverse inequality. And so this is our result. The first result is suppose that Q is on Rd and contains at most k points. We take k plus n subspaces such that the orthogonals are, the intersection is empty. And then we have that we can bound the total variation by the sum of the total variation of the projections. In particular, there can be one-dimensional projections. And I will not talk about proofs, but the proof mainly make use of this lemma that bounds the probability of a point in terms of the maximum of the probability of the projections. Okay. Well, the other result is the following. If we know in advance which is the support of the distribution, then, as I told you before, we need only one single projection. And the condition is you have two probability measures supported on E. E is known now. And let H be a subspace such that the intersection between the orthogonal and I minus I, this is the space, is 0. Then the total variation is equal to the distance, is equal to the total variation of the projection on one. It is a set of all elements that are a difference between one element here and one element here. Yes, in particular it includes 0. Okay? Okay. So this is what I like most. And this is an example. This is the case where we have on dimension 2, we have two Bernoulli distributions. Then the set E is just these 4 points. So these red lines are the only 4 directions that are bad. Any other direction provides the same result. Of course, when we go to statistics, then we don't know P and Q. So we have approximations from Pn to P, Qn to Q. So there will be not very good directions and better directions. Okay. It's clear up to that? Yeah?
Okay, so you will have a lot of points in each one of these 3 group things, or 4. Yeah.
Yeah, we can take any other direction and will work. So if you choose at random a direction, it will work.
So you will get an empirical distribution on the green points.
Well, here there's no empirical distribution, no?
No,
Yeah. Okay. Well, total variation is a strong notion of distance. No? It's more probably the more stronger one. And we would like to see if we can apply it also to some other distance. And I sent Antonio some results that are false a few weeks ago. So both results are false if you use Wasserstein distance or if you use Prohorov distance. Moreover, both results are false if you use any distance that provide with convergence. Unless you put additional restrictions. And I send you a wrong proof. Okay.
Still have it, so I publish it.
Okay, but it's not so bad because, for instance, for Wasserstein distance that we will use in some of the applications, that for one-dimensional distributions is just this expression. We have some inequalities, but it depends on the diameter of the space. So if you put further conditions, then the result will work because you have the bound for that distance. Yeah? So it's not so bad situation. Yeah? It's false for all distance that provide weak convergence, but if we add, we have these two inequalities on both sides. See, in the second one, this is this one is not so bad because it just take the diameter of the set. This one it's not so nice because it includes the minimum distance between 2 points. So if you put this on this side, you don't get nothing too good. Okay. 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 Well, then I turn to statistics. How to apply these results. And well, what I call Mallow's distance between histograms is just Wasserstein distance between the histograms. But people call Mallow's distance when you reduce it to histograms. Okay. Well, discrete tomography was introduced by Sheps in '94. And focus on reconstruction on binary image based on finite sets of projections. So we have a set E in ZD, be the domain of the binary image. Typically they are two-dimensional. And consider N that is the cardinal of E, and F a subset of E. So we want to try to identify F. This is a space, and we have an image inside on this grid. But we only have access to the information that gives on parallel lines orthogonal to certain directions. So the only thing you are able to see is the projections over some directions and how they fall down. So given a direction u in the unit sphere, and we have a set F, the X-ray provides the number of points in the set of lines parallel to u. That is LU stands for the line through the origin parallel to u. We are given with this function. How many points? And it's curious, but probabilistic has not studied this kind of process. Okay. Yes?
X is multiplied by a vector on ones. Because X
No, X is on R.
and U,
Yes, is a
which
with our lines all parallels. LU is a line through the origin parallel to U. Okay? So you have a picture like this. Given a direction U, we estimate based on an histogram built from a partition of the line. So for each direction, our sample will be histograms, like that. So we move U in any direction, and we get a different histogram. So Shapes was interested in reconstruction, and we are interested in a simple problem. We want to make testing without reconstruction. So we don't want to reconstruct the image, the 3D image, but we want to test. This is a heart that is from a healthy person and a heart from a sick person, for instance. Okay? So it's much easier for us than for reconstruction. But there are results by Shapes that you can reconstruct.
And you see the green things, the green lines, right?
Mm-hmm.
This is what you observe.
Yeah. Yes. Yes, yes. These are the points. And you observe.
No, but you observe the green lines or not? You observe only the projection.
No, you observe only the points. And you, this is just to show that I project this point here.
But you have only one line. Like that.
Yeah. And for each line, I will have many lines. I will move U. Okay. Okay. So next I will introduce a new way to do learning that we will apply then. So we have a training sample, x1, y1, xn, yn, with the same distribution of xi. In this case, the labels y1 to yn are known. So suppose instead of taking values in 1m, take a value 0, 1, so sick and healthy, binary. And then appears a new data, and we want to predict the label. This is a typical problem of learning. Well, I will denote by PL the unknown discrete distribution of the conditional distribution of the suppose healthy ones, and PNL, the empirical distribution that I get to look at this, the training sample, just looking where the y is 1. And it's well known that the best rule is the Bayes rule that is defined as, well, this is binary, no? Instead, I think in m equal to. So if you know the conditional expectation, then this is the best rule. And mainly you are looking is it more probably that that looks like a 1 that looks like a 0. The problem is statistical is you don't know the eta function, so you have to estimate the eta function. Okay. Well, for binary, classification, this is the best rule, explicitly. And if both weights are equal, then it's just looking which of both is more probable. And this is just replacing the empirical distribution by the okay. But now we want to apply to the case where we only have access to the projections. So I will introduce the notation for the projection. I have several lines. J correspond to each of the projections when J varies. And this is the new way to produce a classification. That is, we have two empirical measures. Then what we do is we add to the empirical measures, to both, the new data. And we look at which varies less. So we look for in which of these two empirical distributions the new data fits better. Yes, I added to the empirical distribution. Yes, I consider this as a distribution, that is the one I have it, where I add this point. And I do the same to the other distribution. And then I look which are closer. And then the one and which is labeled, this is moves less. So it in this sense, I say fit better. Okay? What is nice for this is that it works on any metric space. Yeah. Because we are not using Euclidean distance in any place. That distance between empirical distributions. So it worked in very general framework. Okay. Well, what we have to prove is consistency, which means that the expected value of the risk, that is, when you make a mistake, converts to the base error. See, that is the best one. And it's clear that L star should not be necessarily 0, because L star being 0 means that the problem is very easy. Yeah? For instance, if you have the two distributions like this, the problem is trivial. Right? this is yeah. We will never commit an error here, right? But typically, the situation is like this. So always you have a region where you make mistakes. That's why you don't get better than this value L star. Okay. Well, and it's very easy to show that you can, the rule that I mentioned, this is when the total variation distance when I add a point to smaller than this one, and this will be converged with consistence. See? So it will be consistent, assuming that for each, for all x such that p1 is greater than p0. Okay. But we have now the empirical distribution, that are one-dimensional. So we have to work a little bit more. And here is an algorithm. The input is the subspace. Suppose that there are lines. We calculate the empirical distribution. We add the points. And then we calculate, it could be the maximum, could be the sum of the one-dimensional directions, and then classify the point. Okay. Okay. So for discrete tomography, the only thing we had to change is to consider distance between histograms. So we have a discrete image, and we have a set of training samples that are discrete image, and the same, we have a new image, and we want to put a label. So we consider the histogram where you project, as I showed before, and we associate for each sample distribution the histogram. Then we use Bassett time distance between histograms. And finally, we apply Canid's neighbors for the one-dimensional projections. And this is the algorithm. We use majority vote, that is Canid's. And since we are only in binary, we just need to compare the number of y's if are smaller or greater than a half. Okay. Okay. Well, now we will consider an application to multivariate Bernoulli distributions. So as I told you, the difference is that now they are not independent. Marginals are binomial, but you have a covariance matrix. And I denote by delta D the set of all possible distributions in the unit group. Well, in this case, you can find just by adding the marginals, the sum. And now we suppose that we have a sample where each data is a multivariate Bernoulli distribution, and we want to test this problem. And there are a lot of examples where you fall in this model, no? For instance, in medical tests, positive or negative, image analysis, marketing, where you have every marginal is binary, but correlated. Well, in this case, the support is known, large but known. Yeah, because the set of is up. This one. Yeah. Large but known. But you remember that it does not depend on the dimension. Our result. So we choose one-dimensional projections, and we can develop a test for the one sample or two sample problem, just using, for instance, Kolmogorov test or whatever one-dimensional test you like on the projections. And in particular, there have been a study, by Kolmogorov test for discrete data. That is slightly different. And for the two sample problem is the same, no? You project now both samples the same. Okay, so this is standard. Well, so I don't know how. Okay, this is. I will talk quickly about some simulations. We generate multivariate Bernoulli distributions in dimension 5, 10, 15, and 20. All have marginal 1/2. In one of them, there are the independent components, and the other has correlation taking these values. And we use 100 one-dimensional projections. And we compare with some known other procedures like random folders, needle, and we get something, a table. We perform quite well, and take in account that when you use 100 directions with the same data set, then the data are not independent. But then we can use Bootstrap. And using Bootstrap, showing that the Bootstrap theorem works, then you can avoid the problem of simultaneous testing. Well, we are here combining things, but. Well, this is another example. On the left is the image. This is for tomography, discrete tomography. And you see that on the second one, we had a noisy thing there. And you know that this is a hard problem in learning, no? Especially if you use networks, deep networks. because there are several examples that you have an image, like a stop signal on the root, and you put a small set, I loved Mary, very small, and then it says, this image is a horse. So deep networks are very sensitive to some slight perturbations of the image because they overfit. When you use several how do you call it? Layers, then you are overfitting. You are producing very, very small cells, and in most of them you have only one point. Okay, but this is a different problem. Okay. Well, and it works well. And the second scenario is this one. We increase the diameter of this image, and the misclassification error was very small, to 55% in the first scenario, and the second 6%. So it works quite well. Oh, I don't know if I... Okay. Well, this is what I don't want to talk about, because I don't understand it. That's why we have co-authors, no? Okay, this is a real data example. It's a SPECT image. See, what they call cardiac single proton emission computed tomography. And we have a database of 266 images of a muscle region of interest, I don't know, data. Well, what we understand it, this can be reduced to a vector of 45 continuous variables, and then they end with a binary vector of dimension 22. So that's fitting our setup. We have binary vector of dimension 22. We split it into the training and testing sample. So the training, we learn here, and we test with this how they behave. And it works. And you see that it works better when you use more directions, when you project, but around 500 is stabilized. So that's why we need a bootstrap, because all these projections are dependent. Okay. Well, this is another example that we will skip because I want to get to the last one. Okay. Well, we provide some new statistical techniques to treat discrete high-dimensional data set based on extension of Heppe's theorem. We show that if we know it in advance the support of the distribution, then it's sufficient to consider only one direction, although in practice we use several ones. They still work on when data are on Hilbert spaces. Okay. and what we use. And this is a problem for Antonio. This was a question that a referee asked, and we don't solve the problem. So the question is, suppose we have, instead of a discrete distribution, we have a signal given by the sum of a small stochastic continuous time signal plus a discrete distribution at some instance of times. And the spikes was written by the referee. So we have these spikes and noisy things. Yeah? And the question is, there is some way to extend the previous results to this more general setting. So the good news is that we have a recent result that for ellipsoidal distribution, continuous ellipsoidal distributions, on also a finite set of projections determine the distribution. But you need that both are ellipsoidal. That both distributions are ellipsoidal. So like Gaussian multivariate normal distributions. So the question is, as far as I understand, if you discretize time, so spikes can only work on a grid, and you have your noise that is Gaussian, a multivariate normal on this setting, but a very small noise signal. Can you extend the results that work for the signal by noise process? Okay, that's all.
Thank you very much for nice talk. So, Antonio.
Please show us again the box plot. So it stabilized around the 500.
Yeah.
Do you think this is somehow related to the Johnson-Dennis theorem?
I don't know, because many people use as alternative the Lindenstrass result, but if you fix epsilon, you need a very, you have to project on a very high dimensional space. Still, you reduce dimension, but not so much depending on epsilon. See, what is nice with this approach is that we reduce to dimension 1.
500 dimensions here.
No, 500 directions.
But yes. Somehow.
Well, no.
You got to remember old paper. I was looking at our joint paper. And
Yeah.
And then in an old paper of you, paper with Cuesta, said
Yeah.
there is no theoretical reason to do more than one projection.
Yes.
Between the end we did, I don't know.
Well, but the problem is, yeah. No, the problem is this. If you know the distribution P and Q, then one direction will do it. The problem is that we don't have P and Q, we have Pn and Qn. And so for Pn and Qn, some directions could be much less informative.
You don't touch the bad directions. Well, so you have
Yeah, but
few.
yeah, but there are directions where you split very different the two distributions and directions where they are mixed. In both cases, they are different. But we have no way to choose an optimal. This is an open question. can you choose in some way an optimal direction instead of taking too many ones. Yes.
First you do an histogram, so you reduce dimensionality first with this
Yeah.
histogram, you quantize it in, with less quantum that was before by doing this histogram, and then you are making your projection of the histogram.
No, then
Where is histogram exactly?
no. The histogram is now a distribution on the line, no? It's already.
Yeah, but before you project, you had a sum of direct mass, which is all the projection, and then you transform that into a histogram, which basically says that you have that many direct masses in this bin, right? Of this.
But this is because it's the only information you have.
So you have no choice on the size of the
Oh, sorry.
bin in the histogram?
No, we don't. No,
It's given to you.
we choose, arbitrary in our example, but by trail.
There is no equilibrium between having a too small step of the bin, so that basically when you have a new observation, it's a completely different
Yeah.
one, and then your total variation.
Yeah, I understand. Yeah, we just look.
Okay.
But yes, it's an open problem, nice open problem also how to choose the beans. And the beans can change depending on the direction you are projecting. So, yeah.
Leonardo.
Sorry.
No.
You have another one? Oh, okay. It's just you said several times bootstrap, but I didn't get what you were bootstrapping.
I'm sorry?
You said several times bootstrap, but I didn't get what you were bootstrapping.
You can read it on the paper.
It's a precise.
No, we use a very general bootstrap theorem that is fantastic. But we have the reference paper. Yeah. Yes, you want to?
The quantitative theorem, when you have infinite, countably infinite support or very large support, and you knew that you could select a smaller support with large probability, would you have some control over it?
Yes. The distribution could be not necessarily finite, but the restriction to be that you don't cut I minus I is strong. So, this is what you. This condition. If the support is large, become harder. Hmm? Yeah, is that your question? Yes. If the set is infinite, this could be a hard condition. Is it finite? No problem. But
I have a question.
Yeah.
So previous slide.
okay. Yes.
No, the other one with the picture.
With the?
The picture.
Oh.
Well, this one. So I look at this picture and say, I think, okay, if you have a bijection between the blue and the green points, then you are done, right?
Mm.
This is the secret.
Yeah.
Okay.
Yes. Yes. Yes, and in the and for instance, for ellipsoidal in dimension 2, it's enough with 3 directions. If you want to do classical statistics, you need to estimate 5 parameters.
So when you have an hypercube,
Mm-hmm.
then you don't want all the parallels
Yeah.
to the.
Mm-hmm. Yeah.
Any other question? Okay, so thank you all the speakers today. ¿Eh? Sí, algo invertido. Después en algún momento, pero esto se entendió bien. Sí.